Let me know if the signal doesn't get to the microphone, so I will raise it a little bit. So just to give you a bit of a background, I did, I guess, part of my education in Italy, Canada, Switzerland, and then back to Canada again. We're actually leading right now a part of the research team inside of Google Canada near Toronto in Waterloo. And to give you an idea of what I'm going to talk today, I'm just going to give a quick overview. So I'm going to show you a little bit of the sensing algorithm that we have, and we're actually going to get back to it later. We're going to talk about rigid registration and ICP, which is one of the core algorithms to address these problems. I want to actually discuss a little bit what I call the monocular Hausdorff distances, which are a way of measuring how good your alignment for rigid registration is, because I think it's actually quite key and often misunderstood whenever I read papers. And then I'm going to focus on a bit of an application, which is actually articulated registration, which was my core research area for the past few years. And I want to conclude actually with something that connects to the past talk from Pierre, which is robust registration. Actually, it's the comment from Keenan that he made earlier in terms of how do you actually produce a real-time registration system that is robust to outliers. And the way in which we will do it is that by relating it to compressed sensing and robust norms. So we're actually going to cover that part as well if you wanted to have some continuity with respect to Pierre's talk. So just to give you an idea of what kind of input we typically use, so these are called RGB-D sensors. Right, I don't have a mouse. RGB-D sensors, and they give you actually two types of media in output. So they're not just traditional cameras that give you color, like the first image in the top, but you actually get a measurement of geometry. Okay, so this is actually a point cloud, or you can triangulate it into a coarse mesh. And the sensor is actually measuring the distance in between the image plane of the camera and the point that you're measuring in the pixel. Okay. Now, if you actually look at the progress that we made with RGB-D sensors over the year, this is actually the state of the art in 2008. It was actually a lab setup, which you can see given the complex rig right here. And we actually moved on pretty fast in actually having affordable solutions into the market. This is actually the fantastic work that first Microsoft started with the Kinect, and then Intel continued with the RealSense line of products that really made consumer-level RGB-D sensors available on the market and across OSs, which is not something that you can underestimate. So, given this type of data, what can we do in terms of registration? What is the registration problem? How is it defined? So let's assume that I take one of these sensors and I go in the wild and I take a snapshot of this statue right here. Right? So if I make a measurement of the statue, I might obtain these two detached pieces of geometry. They're detached because every time that you take a snapshot and you move, the data that you're measuring lives in the coordinate frame of the camera that you're taking it. Right? So what you want to do is that you want to actually reverse engineer the transformation in such a way that you can align or you can register these two surfaces together so you can obtain a complete model. So this is the pairwise or scan-to-scan basic form of the alignment. We have a second one, which is scan-to-scene. So what you do is that you have some digital representation of some scene stored in your hard drive, and now you have a new measurement from the sensor. And to be able to include the new data into your reconstruction of your environment, you want to first align that frame into this coordinate frame and then merge it. Okay, so that's another type of registration. Another one, I can give you parameterized template registration. I can give you here in input a depth map and a color map. And now, given a template of what human faces look like, which you can see right here, that's just a triangular mesh that has been aliased by the screen. So if you zoom in and squint, you can actually see some triangles. And what I want to do is that given these two channels of information, I want to find out the combination of those shapes that actually create the shape of this person in this particular expression. So that's a registration form problem as well. And actually, today we'll discuss most of what you need to do for this kind of problem. Now, let's go back to the pairwise registration problem. So we want to align some model, and I will call this the source model, X, to some target model, Y. Okay, and typically what you do is that you keep one of them frozen, so you only have to optimize one of them, although there is variance to this, so to contradict myself. So for example, in this case, I define a new surface Z right here, which is it's still yellow, but I guess I could have changed the color. And it's a transformed version of the base mesh X. Right, so the problem of defining, or the registration problem in general, can be defined actually as finding the transformations that you want to apply to some base piece of geometry, so that once you apply the transformation, the two surfaces agree. Okay, so to give you another example from the one we said earlier, so we have some X in this case is the REST template, for example. Y are the channels from my RGB-D sensor. And what I want to do is that I want to find a transformation T that, for example, blends all of these shapes together to generate a template that matches the measurements both in geometry and in color. Okay, so you can see that there is a recurrent pattern in what I'm showing you. And now we have two main questions to resolve this problem. So the first one is, how do we measure the quality of the alignment? So if I give you a candidate transformation T, can you tell me whether it's good or not? So that's our fundamental one. And the second question that you have is, what transformations do you allow the model X or the source X to be transformed to match to Y? So let's delve a little bit in those. So there is actually a lot of problems that you run into with the registration when you try to answer these two questions. And these issues are caused by the fact that sensors, as Pierre was mentioning, in particular depth sensors, have an amount of noise that increases as you move further and further from the camera. It's actually increasing quadratically. And or polynomially at least. You have actually problems of partial matching, right? So you cannot overlap the two surfaces perfectly with each other, and you're going to have some parts of the surface, which are the ones that you see here in yellow, which don't have a corresponding point on the green surface. So it's hard to say whether those two surfaces are actually in correspondence or in matching or not. You have ambiguity problems. This is actually a depth map of a hand, right? It's kind of hard to tell whether it was facing forward or back in this case. And finally, although I'm not going to cover that in detail today, you have also illumination changes, right? So if you're using the color map as well, then you have to account for changes in illumination, so maybe you have to estimate the illuminant and so on. But this is an vision conference, so I'm going to skip that part. And I'm going to focus on the geometry, basically. That's the entire point. So now let's go back to the registration problem. So what I can do is that to address all of these issues, what I can do is that I can take my high-level task of finding a transformation, and I can re-express it as an optimization, right? So I want a minimizer of this registration energy, where in input I give it the source model, the transformation that is applied to the source, and the target. And I want to minimize this energy. So now let's take a look at what this energy looks like. Typically, there is two terms to this energy. The first one is the matching energy, or the alignment energy, or the correspondence energy. You can call it in many ways. But the matching energy, what it does it do is that given the transform model X and the target model Y, it tells you how good of a job you're doing. So you have to boil down all this knowledge to one floating point number, essentially. Okay? And the second part of my optimization, on the other hand, would put a conditions on the transformations, right? So it's a prior on the type of transformations that you can apply to X so that it becomes in good alignment with Y. Although you have no idea of measuring. As you can see, it doesn't depend neither on X or Y. It only depends on T, right? So you're only specifying what is allowed to happen. So let's take a look a little bit at the matching energy first. So we said that, yeah, these three terms are here. And one way of abstracting, which I particularly like, is via this integral, right? So I have a piece of geometry over which I'm integrating something. That's my source object. And what I want to do is that I want to take the points X on this source piece of geometry that have been transformed by a transformation. And then I want to measure the distance as measured by this distance function phi in between the transform point X and the surface Y. And by the way, when I use curly symbols, I typically refer to a manifold. And I assume that it's a mathematical manifold, completely smooth and parameterizable and so on, right? It's just a way of abstracting the entire thing. Well, whenever you use uppercases are usually matrices, and small lowercase bold are vectors, just to give you a bit of notation that is consistent around the talk. Now, what does it look like? So I have some surface X and surface Y. I generate my, oh, come on. Does it appear automatically? Yes. I generate my transform surface T of X, and now I need to define a way of measuring whether this alignment is good or not. Right? So I need a metric to do that. And we'll see in a second actually how we can do that. I don't want to spoil a little bit the process. Now for the prior, on the other hand, you can actually do several things, clearly. So if you are trying to match two frames that are rigidly in correspondence with each other, then I can put just a rigid prior onto the system. If I'm trying to, for example, align two objects where the two objects can be an elastic deformation of the two, I can put an elastic prior, like a Timms plate parameterization of the bending energy, of the deformation energies. If I have an articulation, what I can do is I can specify that the object can be perturbed by a set of rigid transformations rather than being one, like in the rigid case, or I can have a composite phenomena where it's too complicated to parameterize the deformation. So what I can do is that I measure some data that contains the class of transformations that are acceptable. And this is the case that happens, for example, for face tracking or dense body tracking. And then there is things for which building a parameterization of transformations is a bit hard. You will have to solve for an inverse Navier-Stokes equation if you want to do this, which is, it's not the easiest thing to do in the world if you want to do registration. So that problem is actually, amongst this class, is probably the one that has been addressed the least. I am aware of only one paper that works on that. Now, these are actually just the priors, so you can have rigid, elastic deformation, piecewise deformation, data-driven. We'll see a few of these later. Now, we have the general form, right? So we have this optimization problem, we have the matching energy and the prior energy. So what I want to do is that I want to start from a simplified version of the problem. So, and this is actually part of the rigid registration class and the ICP, which is one of the algorithms that allows you to solve for this. So now the idea is that if I give you these two pieces of geometry, and let's say that I give you these 5 vertices on the two surfaces, and by the way, these are the only knowledge that you have about the surface, right? And they're literally located in 2 different embedding in R3, or in 2 different locations of the R2 or R2 embedding in this case. And the only thing that you provide to the registration algorithm is that you say, well, the ID or the name of these points remain consistent. So you know that xcon 3 is mapped to ycon 3, you know that xcon 2 is mapped to ycon 2. And now what you want to do is that, can you please tell me what is the roto translation that takes the shape right here, rotates it and translates it so that it's in overlap with the second one. And if you're doing a perfect job, that's what essentially what you expect, right? So, and actually when you talk about registration algorithms, this kind of visualization is pretty common. So what is happening here is that the lines are aliasing with respect to each other. So if you have a very good alignment, you're going to see a little bit of the target surface and a bit of the source surface. So this is a very typical way of visualizing. It's actually emergent behavior, but it's actually what everybody uses to show that things are in alignment, qualitatively at least. Now, we have a little problem with this shape matching, which is actually we want to compute this rotation and translation, this arrow that rotates this transformation to align the 2 surfaces, right? So what we can do is that we can express it as an optimization problem. So let's start from that. So what I can do is that, do you agree that this is actually the optimization problem that we want to solve? So we want the rotation and the translation, okay? The sum is over all the set of points. Right? You need at least 2 points in this case to give you a rigid rotation and translation. And what you want to do is that you want to transform the source geometry x. And right now I spelled out the transformation. I said that I take one of the vertices and I rotate it by a rotation matrix R, and then I translate it by a vector t, okay? And notice that there is xn right here and 1n right here. So what I can do is that I take the deformed version of x, rxn plus t, and I want it to be close in an Euclidean sense to the point yn. So this is the matching energy we were talking about before. There is a second part to this optimization problem, which is that I'm assuming that I want a rigid transformation. Right, so T and R is a 2x2 matrix in this case. T is a vector with 2 entries. There is nothing in this optimization that, well, until I place the term right there, there is nothing that says that R should be something different from a rotation. So what I do, I put a prior on the transformation, or a prior on the optimization. So what I do is that I insert this indicator function that will give me infinity, right? So some function where I plug in a rotation matrix R, and it will be very unhappy if I give it something which is not a rotation. So this is a way of, by the way, of encoding a constraint saying that R wants to be a rotation matrix. In this case, I'm asking it to be part of the SO3 group, or SO2 in this case, considering the example is in 2D. Now, how do you actually solve this? Well, this is just an optimization problem, right? So you can do what you learn in calculus. You take derivatives through this energy, and you vanish them, and you try to find the solution. And actually, if you actually look at so I'm not going to go through the proof right here, but if you actually look at this technical report, differentiating through this function is not that hard. Well, I guess before procrastination analysis was discovered, it was hard, but it's pretty common these days. And the solution of this problem is actually relatively straightforward. So the first thing that you do is that you compute the mean of the 2-point sets, that give you the correspondences, right? X bar and Y bar. So this is just a arithmetic mean. And then what you do is that you demean or create the barycenter version of the point set, X bar and Y bar, okay? And it turns out that the optimal translation vector t, as you differentiate through the energy that I showed you earlier, is given simply by this expression. As you can see, we have Y bar and X bar, which are just the barycenters, and there is a rotation matrix that we're going to touch in a second. So if you differentiate through the expression with respect to t, that's the solution that you get. Now I can do the same thing with respect to rotation, and the solution of the problem, again, is not that hard. What you can do is that you can stack all of the vectors in a fat matrix. So you place all the vectors vertically in this case, in these 2 stack matrices, X bar and Y bar, and these are the d-mean point sets. And once I have that, what I can do is that I can compute the covariance or the SVD decomposition of the covariance matrix implied by this point set. Okay, so what I do when I do that, when I get that, is that I get these matrices U sigma V. By the structure of SVD, I know that U and V are orthogonal. If the matrix is symmetric, U and V are going to be the same, if I'm not mistaken. And sigma is going to be a diagonal matrix. Okay, so now to actually compute the optimal rotation, as you will find out, as proven in this paper, which is actually the nicest explanation of the entire thing, the solution of the optimal rotation is nothing else than concatenating the matrix V with the matrix U with one small change, which is this sign, essentially. So these matrices are orthogonal, so this is going to have a unit determinant, and it's going to be simply a sign that avoids the problem from flipping on itself. So sometimes whenever you solve that problem, it might happen that if you just take V and U and you forgot that term, you might obtain actually the flip transformation. But this is just to show you that for this very simple registration problem, where the transformation was belonging to a certain class and correspondences were given to you, we actually have a closed form solution, which is great. Now, the problem is that you cannot take this and really extend it directly to more complex optimization problems. So that's actually the core of most of the talk today. So now what do we do? So we have assumed pairwise correspondences, and now what if you don't have them? So how can you approach the problem? I give you this initial configuration, but now I do not know that X3 corresponds to Y3, for example, anymore. You have no knowledge at all. Well, what you can do is that you can assume that the initial configuration of your blue shape is close enough to the yellow shape, so in such a way that local registration will actually bring them back into alignment. So now let's see what that looks like. So, well, yeah, that one is not available, so we don't have exact correspondences. And however, as we mentioned earlier, there is a way of designing a metric that tells me, given a configuration of the transform object, how good of a job I'm doing. So that one I can always do. So let's take a look at this metric again. It was this integral. And now because we don't have a continuous surface anymore, we assume that X is actually given as a point set. We can simply replace the integral with a sum. Okay? And now we have a metric that takes, for every point xn, the measure of how far xn is from y. Okay, and this is mostly a notation slide, but the way in which I like to write this entire thing, if you assume that phi is the Euclidean metric, is via this energy term. So you will see this over and over popping up in the talk. So what I do is that I take a bunch of points, x, on my source surface, and there is n of them, and then I measure the distance in between x and its projection onto y, and I measure that length. So you can see it in this figure here. I take x, I project it onto y, and then it's the length of that vector. So why this is meaningful, I didn't tell you yet. So why is it fair to actually pick that projection point and insert it in that energy form? So what I can do is that I can actually write the problem and take a step back. So what I can say is that, well, now rather than having just a rotation and a translation that I'm looking for, I'm going to add a set of degree of freedom to the problem. I'm also going to add the set of correspondences y, so the end point of these dot on the yellow curve. Okay, so I can add degree of freedom to the problem. And now what I can do is that I can take this expression that I have on the right, and I can actually differentiate it in two different stages. So in the first stage, I differentiate with respect, or I only consider y as being degrees of freedom. Okay? And in the second stage, I only consider r and t being the degree of freedom. So what happens if I do that? I obtain these two-stage optimization, which is an iterative algorithm at this point. And in the first problem, so as you can see, r and t are fixed. Okay? And now what I have is that I'm looking for the y's that minimize this distance, and this is the Euclidean distance. And the only condition that I have is that auxiliary variables y are supposed to lie on the manifold curvy y, or on the point set, if you have only a point set representation of y. So this is a way of actually deriving ICP step by step, basically from an alignment metric. So now this is actually a visualization of the same algorithm that I was showing you, rather than with expressions, is actually visually. So I have my surface x, which is sampled via these black dots. The first thing that I do is that I have some way of computing closest point correspondences. We'll go into that in a second. I obtain these vectors. These will give me the point sets. And now remember, shape matching, given a set of points, x and y that correspond to each other, can generate a transformation that align them optimally. Okay, so what I do is that I can actually run just shape matching in this case, and generate a new transformation, which, for example, will bring me in this configuration, which might be overshot in this case, but it doesn't matter. And then I can repeat the process. New correspondences, and then new transformation, until I hope to convert to what is the global optima, although I have no guarantee of it. Okay? So this will only give you local convergence properties. Now, this is just a visualization of what we just described, basically. Now, the question is that if I assume that I split the problem in this particular problem, then I have to compute correspondences, right? So I could do it in brute force. I could just span the entire target surface and look for the closest point, or I can use other techniques. For example, I can use spatial data structures. I can use, for example, acceleration data structure that organize space, and typically these have a n log n cost to assemble and log n cost to query. For example, a KD3 is one of the structures, or the even more regular version will be an octree, okay, with different characteristics according to what you want to do. But this is actually as a if you want to do real-time performance, n log n is actually not that small of a number. So the constant in front of that is also not something that you can ignore. Or the other way of doing it, which is actually what is used a lot in real-time performance, is something called projective lookup. So I don't claim to be able to reorganize the entire space at each iteration, because I will have to rebuild one of these KD3 for a new depth map, for example, at every iteration. But what I do is that I work under the assumption that my camera, okay, brings these two surfaces into quasi-alignment. Like in this case, right? They're not in perfect alignment, but if I look through the two surfaces from the same viewpoint, I can actually establish correspondences. So for example, for that point right there, okay, I can say that rather than having the correct correspondence being pi on y, the one that I drew, I can actually say that this approximate correspondence pi tilde is going to be the correct one. And you can see that in the limit, so when the two surfaces are actually into alignment, this is the correct choice. So you always want to check for that to be the case. Like I'd say, like whenever you write an optimization problem, if your optimal solution does not or moves, you're in a bad state. You've done some mistakes writing your energy. And doing this projective lookup is actually not that difficult. So one of these two surfaces will be the depth map, which is already in the coordinate frame of the sensor. So what you can do is that you can take the other one, for example, the blue one, which is your model. You can render it, or you can query, for example, a point. For example, one of these vertices x. You can compute the ij coordinate of the vertex v in image plane, and then you can just measure the distance on the depth map. And clearly, this is just an O1 lookup into memory. And if, yeah?
I don't have a ton of experience with the depth maps, but some that I've seen, they'll just have like giant parts where there's no depth.
I'll get to that. That's part 4 or 5 of the talk, yeah. So there is actually a term explicitly, or a way of dealing explicitly with that problem. It's the robust part of the talk. If I get there, there's no guarantee, but yeah. Yeah, no, it's fine, don't worry. So the other way in which you can do it is that, for example, if for example, in some domains, which we'll see later, it's actually completely reasonable to brute force the problem. So for example, let's say that I'm trying to align this point, maybe it's a collection of circles, to this collection of circles. What I can do is that I can simply brute force project the point on all of them, and I can simply take the shortest of the three, right? So if you don't have that many yellow, in this case, circles in your problem, you can do this quite efficiently. And we'll see why later this is important in the case of end tracking, which was kind of like my core research. And as you can see, if I have a triangular mesh with, I don't know, like tens of thousands of triangles, if I brute force through the process, it will be pretty slow. But if I can represent an entire mesh or an entire geometric object with a few primitives, I will not incur into that cost. And this is actually quite commonly done. There was actually a paper at CVPR like 2 weeks ago that was still doing that on triangular meshes even, so which is playing with fire a little bit, I guess, in terms of performance. So now another part that is very important. So we're going to do a little switch right now. So we talked about correspondences, and now we're going to go back to the metric. So if you read through the literature of registration, I assume that not very far into it, you will find something that's called point-to-plane versus point-to-point optimization for registration. And we'll see what the effect of this is later. So that it means that, what that means, it means that the metrics that we wrote earlier, that was written in this form, where I take a point, project it onto the yellow curve, and then measure the distance in between 2 points, is actually often replaced with an expression of that form, where I take the point, and rather than measuring the distance to the surface, I measure the distance to the tangent space of the function, or of y, sorry. So you assume that the closest point correspondence is going to be equipped with a normal, and then I measure the distance from the tangent plane defined by that oriented point. Now, this is great, as we'll see in a second, but what I want you to be aware of is why this actually works. Because actually the geometry behind the problem was studied in the early 2000s by Potman and then Mitra, and is actually quite interesting, and I think it's worth going into. So I'll give you this simple example where I'm trying to align. So the blue samples were sampled from some geometry I'm registering, and now I actually have a continuous function, which is just this segment right here. So it's a continuously smooth function. It's a little planar piece of geometry. And that planar piece of geometry was sampled again by those points. And I'm trying to perform the registration in between those two sampling, okay? And now what I can do is that I can actually do the point-to-point metric, okay? So if you're doing point-to-point metric, what you're doing is that you're querying the function at the blue points with isolines that look in this form. Now, as you can see, if I am, the more and more away from the surface I go, the better this function is an approximation to the correct one that you see up top. Do you agree? Right, so in the far field, I have a good approximation of the function. But if I actually go close to the surface, right here, you have this bumpy surface that Pierre actually was mentioning as well, and it's a terrible approximation, right? Because the distance function look like that in the neighborhood, not like that at all. So when you're actually doing point-to-plane approximation, so what you're doing is that you're actually constructing, and that's a point for later, but you're actually constructing a better approximation of the square distance function in a neighborhood of the point set. And there is actually this paper that I mentioned down here from Florianhofer. I think there was another one from Potman, and another one from Niloy. So this one is, I guess, the latest one. But it can show you that if you actually take a quadratic expansion of the sign distance function, which is what we will need later to do optimization, point-to-plane and point-to-point optimization emerge out of the process. You don't have to say, oh, this is what I pick. This is not random, the fact that point-to-plane will converge better. So point-to-plane will converge better because what you're doing is that you're doing Gauss-Newton of the square distance function. So you're computing an expansion, a Taylor expansion of the square distance function at a certain point. So you're doing Gauss-Newton rather than doing gradient descent. That's why it's converging better. Now, this is actually a figure from this paper from Simon or Sismon. I never knew how to pronounce it. But that actually shows how fast the error decays in the two processes. And if you actually analyze this properly, the point-to-point convergence will be linear, while the point-to-plane convergence will be quadratic, so it will converge faster. So if I give you an example of this, what I did is that I displayed the two animations that I will play at constant frame rate. So at every frame, both algorithms run on one iteration, and you can actually compare the convergence speed of the two algorithms. And exactly what you expect happens. So the point-to-point, as you can see if I replay, at the beginning start converging really fast, but then it completely stalls. Why? Because once the two surfaces are in almost perfect alignment, I'm using the wrong approximate of the sign distance function to do the alignment or to measure the metric of my alignment. On the other hand, point-to-plane, while sometimes cannot be particularly stable, is actually picking the near field approximation of the sign distance function. So especially if you initialize ICP with something that is close to your solution, that's actually why point-to-plane is working particularly well. Now, as you can see right here, though, point-to-plane has a bit of a null space. So if I put the blue points along this horizontal line right here, they will all give me zero residual. So they're all optimal transformations of those points that maximize my alignment or minimize my alignment metric. And actually, in practice, often people mix these two metrics together to obtain the stability of point-to-point and the near field approximations of the point-to-plane energy. So you find also hybrids in between the two. And I think the paper from Niloy is actually the only one that I saw in the literature that does this properly. So I think it's the SGP 2004 paper from Niloy Mitra that actually shows how these actually should be actually mixed optimally to get a real quadratic approximation of the SDF. So if you want to get the cleanest version of ICP, you actually find it in there. Is there any question, by the way? You can interrupt me any second. No? All right.
Maybe one. So the plane where they come from, because in some cases you would have a triangle mesh.
Right.
And then I guess the best thing is to just compute the distance to the triangle. So I'm assuming here that you don't have a mesh, but the planes are estimated somehow.
Right. So that's an excellent question, especially because your question might be on top of a plane. Do I actually need a sign for the normal? So let me answer the second part of the question. You do not need a sign for the normal, because if the normal is flipped, the only thing that changes is the sign of the expression in input to the norm, so it will be discarded. So that's the first. So I'm fine with having an unoriented mesh on an unoriented point set, which is a pretty big advantage in doing this. And the second part is that if I am on a point set, I can actually do just normal estimation. So you can do normal estimation by using the grid of the image from the depth map, or you can compute it via local estimation, for example, querying your neighbors on a KD3 and so on. So those are the two main ways of doing it. But often nowadays, there is not that many papers that work on unoriented point sets. as Pierre was mentioning earlier, and as we were discussing today with him, you pay a price whenever you do an optimization on something that does not have normals. But they're not extremely challenging to compute if you want. It's actually very similar to the registration problem in terms of math. It's this a similar optimization in terms of covariance and SVDs that you have to do.
What if you just use like gradient or the vector between x and the different pointers you're drawing?
So that will work in the far field, right? Because in the far field, you will find a point which is exactly the point on the map. Yeah, you can do that. And actually in the 2D part of the registration that we had, so the 2D ICP, to do image-based alignment, that's exactly what we were doing. We were assuming that projection vector to be the normal of the problem. And it works like a charm. The only problem is that when you are close to the point itself, then you have a zero length vector. So you have to be careful on what you do there. But for the rest, and I think the way in which we resolved it is that we only use that to guide you toward the solution, and then the last little fraction we turn it off. Yeah, if you want to go into the details. All right, so that part is done. Okay. So, all right, so now we have different ways of writing the shape matching energy. We know how to compute correspondences, but there is actually a pretty big limitation, right? So if you looked back, actually let me roll back a couple of slides, which means that I've lost my time count now, and my mouse. So if you look back at this alternating optimization, okay, we knew how to solve the second problem in specifically this class, right? So the shape matching problem with SVD, as I showed you earlier, works only if you have some point matching to some other point constrained to be a rotation matrix. It doesn't generalize very well to more complex problems. Okay, it doesn't generalize, for example, to elastic deformation. It has to be rigid, and you have to act for correspondences. We solved the correspondence problem, but we did not know how to approach more general type of transformations. And now I'm going to give you an example, which is actually, I'm going to apply to the rigid problem, but it's completely generic. So what you can do is that you can take your transformation, and you can linearize the objective function. So let's do it for the rotation case. So I'm going to take a linearization about the origin. So I want to do Taylor about the origin, not in an offset. So I'm going to center my rotation at the previous iteration, right? So I basically expect this rotation matrix R tilde, which is going to be the objective of my optimization, to be close to identity, okay? Or to have parameters that are close to, rotation parameters that are close to 0. Now, if I do that, right? So if I write a generic 2D rotation matrix, that's what it is. And if you actually take in the limit for theta that goes to 0, this actually becomes a linear mapping, right? It becomes a linear function between the parameters and the content of the matrix. So what I can do is that rather than optimizing for a matrix with particular characteristics of it being a rotation, what I can do is that, given that refinement, I can actually optimize in the tangent space, right? So somewhere in the neighborhood of the origin. And in practice, what I'm doing is that I'm approximating the trajectory of this blue point that is rotating along the blue curve with just a straight line, which is tangent to the circle. If you want to look at the geometry of it, it doesn't really matter. And now what I can do is that I can convert my optimization problem, which before was in closed form, right? So given correspondences, I can compute the rotation and translation. And I can actually solve this in an iterative way, right? So I'm looking for the parameter theta, which is actually a perturbation parameter. So this will be really a delta R parameterized by theta, okay? And now this is actually a linear optimization problem, with one change from what we were looking at earlier, except for the parameterization and the fact that it's about the origin. And that change is that I'm also asking for these thetas to be close to 0. Because if I do that, then I'm working in the assumption of the Taylor expansion of the matrix R. Do you agree? Right? So if theta is large, these will be very unhappy. But if theta is large, these will also be very wrong. Right? So I penalize large transformations in between iterations. And now what I do is that I have something which is completely generic. Like in this case was for the rotation, for the rigid transformation problem. But I can always do that. If the function is at least differentiable once, I can compute the gradients of the functions, which I guess it's boiled in there. And I can compute actually linear mapping in between input and output. And this is what Gauss-Newton, if you have done it in your optimization courses, does all the time. So this is the Gauss-Newton or the LM version of the problem rather than the SVD version. Yeah? Because otherwise your Taylor expansion is off, right? So Taylor is good about the origin or about the point at which you did the expansion.
But why can we assume that we are not looking for a bigger value of theta?
Because this becomes an iterative optimization. So you're going to compute the next theta, and then you update your RT minus 1. and then you repeat the process again. So it becomes, it's not a closed form solution, it's an iterative optimization algorithm, just like your gradient descent, right? You don't take just one step of gradient and you get a solution typically. You have to run multiple of them until you reach the optima. So it's the same thing here.
Okay.
So it is not in closed form anymore, it's iterative, but it has nice properties in the sense that I can actually feed it whatever I want through it, and it will still work now, in terms of the expression of the energy. Is that clear? Yes. Yeah, so that's that comment that was that you were asking about. So now we have this framework where I can actually perform this process on whatever energy I want as far as it's differentiable, right? So we're gonna have some matching energy, some prior energy, we're gonna have our initial configuration, which I call zeta 0 in this case, and then iteratively, I'm trying to deform my surface so that it matches my target surface Y, right? So after t iterations of registration, I want the two to be perfectly overlapped to each other. And I guess I didn't follow my standard of overlapping the two channels right here, so sorry about that. And in the case of rigid transformation, that's exactly what this looks like, except that I forgot a t right there, but I guess it doesn't matter too much. So you have your matching energy, which in this case I use the point-to-point optimization, which we saw earlier, and then, which is the matching energy, which is the first one. And then you have the prior energy, right, that says that my transformation Z is supposed to be a rotation and a translation of X. Do you agree that now this is boiled down back into the original framework of looking at the problem and describing how do I say that things align and what type of transformations do I accept? Okay. So now we have, and I have no idea of the time because my clock has reset. Okay. So now we understood a little bit the sensors and why they give you this data. It's a geometric problem, you want to align things. There is a way of aligning geometry either in closed form if you have correspondences, or there is an iterative way of doing it by if you have some correspondences given to you by somebody, or you can use closest point projections to compute the optimization. And in terms of solve, you can either use SVD if you have a very simple class of problems, or you can actually perform an expansion of your energy and just throw some iterative solver to the problem. So that's what we learned until now. Now what I want to show you is that everything breaks loose or when you actually deal with a sensor, because you know that's life. So let's take a look at on one first example to begin with. Let's say that this is, and sorry if I change the letter, but this is the point that I want to register to the circle. I think I swapped X and Y in this case. It's Frankenslides, I told you. And now I want to solve for this optimization problem. So I want to move the circle so that I actually fit to that point. Okay? And there is a big problem whenever you deal with just the closest point projection pies that we were looking at earlier. So let's consider these two initializations right here. The task is that I want to bring the circle to be fitting in a least square sense to these points right here. Right? So look at the two initializations and what happens. And by the way, the behavior is not consistent because this is a non-convex problem, right? If it was convex, you'll have one solution. But this is an example that two different initializations give you different solutions. In the first case, I ran ICP. Those are the correspondences. One iteration, let's say, bam, I'm done. Okay? In the second case, that configuration is actually a very bad local minima of my alignment. Right? So there is vertically, I'm fitting pretty well. Horizontally, there are as many red lines that pull me to the right as there are pulling me to the left. That's one way of interpreting the problem in a more intuitive sense without having to look at the optimization. Now, what is happening is that you're completely forgetting the fact that those points were actually measured by a sensor. So in this case, these points right here was measured from this point of view. So in theory, there is no way that this part of the geometry could be fitting to those points because that part of the geometry is backward facing, so how is that possible? Something that is backward facing fits to my front facing point. It makes no sense. So one way of dealing with that is actually by performing a simple change to the projection operator pi. And what you say is that you're saying, well, when you perform a correspondence, because you want to find a correspondence that was observed from the sensor, what you can do is that you can restrict the projection to actually only query the front part of your mesh, which is equivalent to saying that you take your model, you do backface culling, and then you compute correspondences. Okay? So let's see what happens in the case. I take my object, I do backface culling, so in this case I remove all of this. Now my correspondences will map to the boundary. That's a feasible configuration, right? Those points are visible from the camera, and then I iterate, and then I converge. Yeah? No, because if you assume that you are in the pathological case, which is actually this one, if you compare the normals on the back to the normals of the samples, they're going to be opposite to each other. So you're going to take all of these points, you're going to see that they're all outliers, and the circle will not move at all. So if you do normal rejection in the traditional sense.
Well, maybe not rejection, but you can look at correspondence, including the alignment of the normals.
Do you see the dotted line? That's what's coming in a second. Yeah, so that's, yeah. In the first sense where you're just throwing away, you cannot do that because you're stuck. But there is another way of doing it, which is actually quite beautiful, and John proposed it back in 2016, but I think it's actually part of the Learn the Shape of a Dolphin paper from Fitzgibbon. And the idea is the following, is that, well, your points y also have a normal. So what you do is that you're searching for a correspondence not only that minimizes the Euclidean proximity to your target point, but also that maximizes the normal matching, as you can see, of the, so z pi will give you the normal of the surface z at a query point. And what actually happens is the following. You can write basically the problem in that form as a discrete continuous search. So let's say you have this point, you want to compute the optimal correspondence of the point on the surface. So the first thing that you do is that you treat it as a discrete optimization. So I give you some source points, target points, sorry, like here. And I can just evaluate an energy function at each of these 3 points, right, for this point yi. And I can take the smallest one of those 3. Right, so I have those 3, I only take the smallest one. So that's the initialization of the problem. And then what I can do is that if I can take this point right here and I can parameterize it on the manifold of this circle, what I can do is that I can optimize for it directly in the registration routine. What it means is that this point right here will be parameterized by these degrees of freedom UI, which will be part of the registration optimization. And this point will be able to move and slide onto the surface until actually I compute the optimal one. Right, so this is called lifting. So you're assuming that your correspondences are not just given to you or computed by closest point. It's still a non-convex problem, the one of finding, as I was showing you earlier. So you cannot just differentiate through it. But what you can do is that you can split, again, the non-differentiable part of the correspondence problem in this. And then if you're in the correct convergence basin, then you can actually run a continuous optimization directly within the registration. It's not that you have to run something separately, right? So you embed this directly into the optimization. It's pretty complicated because basically what that involves is that both the normals, okay, I don't have a cursor, but both the function z pi that gives you the normal and the function z have to be parameterized. And in this case, John was using a loop subdivision surface for which, given a coordinate uv on the, or I guess the parametric position on the surface, you can actually query this point and this normal to infinite precision via the stuff from, what's his name? Joost. Yeah, Joost Stam's theory. So that's how you can do it. It's a bit harder to do. I am actually not always convinced that that's worth the effort because it's actually quite complicated to perform that optimization. You have to make sure that when you swap triangle IDs, your derivatives remain consistent, and yeah, it's a bit of a pain. But if you have a good programmer, you can do that if you want. I mean, there's nothing wrong with it. So now I can ask you the same question. Now we fix this problem of, you might have a better local minima where your correspondences made no sense at all in terms of visibility. Now, are we done again? And the answer will be no again. And the way in which I'm going to start this discussion is by generalizing the registration problem a little bit. And I'm going to tell you, if I have 2 geometric objects, what do you use to tell me if these 2 objects are the same object in terms of geometry, identical geometrically? So that's the Hausdorff metric, right? So if the Hausdorff metric in between 2 surfaces is 0, they're perfectly identical to each other from a geometric point of view. And now the question is like, well, it would be nice if I can use the Hausdorff metric, plug it into a registration framework, and if I get a perfect 0, I'm doing a perfect job, right? Assuming that I have no noise and outliers. So let's see what actually happens. So this is the Hausdorff metric. I'll maybe storm through it. So given 2 surfaces, you compute for all of the points on one surface, the correspondences onto the other, and then you take the worst case scenario. And then you do the thing from the other direction. You take all of the points on the yellow surface, you measure the closest point onto the blue surface, and you take the worst case scenario. You can actually write these in terms of an equation, essentially a discrete optimization in this case, well, continuous if you're on the smooth surface, but there is max and means that are involved. And the thing that I want you to notice is that the argument inside of these brackets right here, we already know how to work with them, right? Because these are actually the ICP correspondences from earlier. So if we can deal with these parts, with these 3 maxes right here, we can actually convert this to be an ICP problem that we can tackle with, Gauss-Newton or whatever other optimization toolbox you want to use. So let's do that. I just unroll the same expression in one single line. And now the first thing that we're going to do is that we know that we can cope with one mean operator in here in terms of differentiability because we can split the problem in this alternating optimization. But we're not very happy about the other three max. So what I can do is that, first of all, it's not going to be just on the continuous surface. I'm going to look at the discrete surface. And the second thing that I do is that I take an average of the measurements. I don't take the max anymore. It will be great if I could use it, but I cannot really differentiate through that easily. Okay, so I just take the average, and then this becomes a least square problem, right? So it's a sum of square residuals, which I can actually cope with it in terms of math quite easily. So we still have a problem, which is the second max. And notice that we still have two terms, one that goes from x toward y, and then one that goes from y toward x. So you might ask the question later on, why in a registration algorithm do you have to have these mutual correspondences? That's why. Or that's how you can actually justify it from first principles. So now we have the second problem, the max. And again, if you look at many registration papers, rather than using a max, again, from max, you go, you go to the sum. So you typically have a blended sum with weights that typically regularize the domain. So for example, if one sum is on pixels, the other one is on geometry, you put in a number that tries to equalize the two dimensions. There is actually other ways of doing it. But that's actually what you have. So do you agree that this is actually derived from the Hausdorff distance? And actually, I can differentiate through this, because now this term right here and that term right there are nothing else than my ICP correspondences that I had earlier. So once I compute them, everything else, I can deal with it in a differentiable way, and I have no problem. So that's what I like. So this is, I call this the differentiable Hausdorff, but it's just a name. It doesn't really matter. And it's our matching energy. And one will go from your digital representation of the object you're trying to align to your data, for example, your mesh to your point cloud in the depth map. And the other one will go from your depth map to your model, right? And you have to be very careful because now you're going to have to run these projections. So they have to be efficient for the entire pipeline to actually be running in real time. So let's go one step further. And I can tell you again, what I just wrote is still wrong. It still doesn't work. Why? Because in the first case that I was considering, and until actually relatively recently, whenever you have one of these sensors that performs 3D measurements in real time, is actually only one of them is allowed, unless they come in a particular setup. So some of them can still kind of work if you put multiple sensors in the system, but a typical setting is that you have a single sensor. You have a monocular observation of the geometry into the system, a 3D monocular, but it's still from a single point of view. So what you have is that even though you have two surfaces that are in perfect alignment, this is the configuration that you obtain, right? So X is the actual ground truth geometry, and let's assume that you have a model for it in the correct location, and Y is the point cloud that the sensor measured. So the hope is that if I now plug in this configuration to my metric, I will get a 0 out of it, right? Because otherwise, it will become very difficult to justify one doing a perfect job. And the energy above doesn't do that. So for the first case, when I go in between the yellow points and I project them onto the blue curve, they are already on the curve, so their projection distance is 0. So the second term is completely 0, and we are very happy about that. And actually, in a lot of papers, that's the only term that you will find, by the way. And the second term, on the other hand, does the opposite task, right? The second half of the Hausdorff distance takes distance from the model to the data. And this is broken because if I take now a random point, let's say that one, right? So there will be at least one entry that is non-zero, for example, this one into my sum. So we're not happy. And now what you can realize, though, is that if I take a look at this energy and I just restrict it or restrict one of them to only consider the visibility of the problem, then we can actually fix it. So let's consider this problem. So it's not the same geometry, and I'm sorry about that, but yeah, it's a legacy slide. So I made some measurements, and let's say that this was the geometric model that fit the samples the best. So you have a local minimum of your optimization. And now I might tell you, nope, that one was it, and nope, that one was it. And if you look at it in terms of the data to model energy, all three configurations give you a 0, right? But now what you can consider is that whenever you selected those 4 points as being the meaningful one in your depth sensor, you also implicitly assumed that all of the ones in the surrounding were not descriptive of your object, up to noise and outliers, but we'll see how to deal with that later, maybe. I might have to do the compressed version of that, but all right. So what we can do is that we can actually change our metric, if my slide goes forward. And what I can do is that I can take the first term, which is the one from blue, which I remove the symbols, one of the two, and I can actually change it a little bit in such a way that the projection is actually not performed in 3D, but is actually performed in an image plane. Why? Because if I'm actually in perfect alignment from the point of view of the camera, if now I overlap the point cloud in my system with the actual geometry projected onto the image plane, I will have a perfect overlap, which means that the first energy will be again 0. Okay, so what I can do is that I can take my, what I called earlier differential of Hausdorff, and I can change my projection operator, rather than doing 3D because I don't have full data, so that will be not a good idea. What I can do is that I can replace my projection on Y with a projection onto the screen space rendering of Y. And what this turns out to be is actually, I tried to look for an image-based alignment for geometry. I couldn't find a decent paper. And this is actually the first time where we were able to write this kind of problem, where I say, I have two objects, let's say I have two spheres, and I want some alignment that hides the blue sphere behind the yellow one. So the yellow one, let's say that is the region of interest of what you're trying to measure. So let's say you have a scanner, you identify you're tracking a person, so are the points that correspond to the tracked pixels. And the blue one is the model that you're registering, right? So in this case, they're clearly out of alignment. So what you want to do is that you want to hide the blue model behind the yellow measurements that you have. And the cool thing is that you don't have to do anything difficult. Like I was looking at vision papers, and there is like 15 different ways of doing it, and none of them convince me. But if you only change that, in terms of optimization, there is only one extra entry in a chain rule that you have to add to your optimization, so it's about 5 lines of code. And the only thing that it does is that it's actually interpretable from a geometry point of view. It's just saying, I want my model to disappear behind my data. So it's an image space alignment. And the other cool thing is that, remember, you want to be able to perform correspondences fast, right? As I was telling you earlier, if you're using cylinders, this correspondence on the blue model is quick, because I can just do brute force in that case, right? But these correspondences of giving a pixel, find me the closest pixel on the yellow surface, could be complicated. And it's actually not. Because what you can do is that you can compute the sign distance function in image space, which you can run in linear time for the yellow object. It will generate a sign distance function image. And now the only thing that you need to do to evaluate this energy is query, again, an image, and you're done. So it's super fast. I think for a 1 megapixel image, it was running in like 200 microseconds, so 0.2 milliseconds. So it was not very important. I need time. Or I can quit my, 55. 45, plus question or minus questions? Okay. So now, so we have the rigid registration part. Now we know how to make the alignment metric to work with a single sensor. Now what I want to do is that I want to take a particular class of prior that describe your deformation, and I'm actually going to show you how to code it. And by the way, at the end of the talk, there is a link that points you to one of the pages for the courses in the past, and we actually have code. So all of the things that I'm showing you, you can actually map them one-to-one with that piece of code, which I think it's kind of neat. So you can actually learn how to do articulated registration in 2D in an afternoon if you want to do that. So let's take a look at what that means, though. So we're actually talking about roughly, well, I guess it could be either rigid or articulated. That's a superset of the rigid case, right? So let's see how that works. Let's take the typical case for articulated deformal of objects, right? So this is the most generic form. This is just a linear blend skinning, right? So you're saying that your deformed surface Z, the one that has been transformed from the source, is nothing else than your source geometry, okay, with a weighted linear transformation applied to it. Okay, and in this case, the parameters of my registration will be these matrices, the one without the bar, the T1 and T2 without the bar on top, right? So if I want to track, if I'm doing tracking, I'm actually optimizing for those. If I'm doing tracking and calibration, I'm optimizing for both those and those in that particular case. And these weights here are typically called skinning weights, and basically decide which vertex listen to what transformations. So if you're not familiar with linear blend skinning, which you might as well easily be, so the T-bars basically define coordinate frames. The omegas define how each point is attached to a coordinate frame, and then the T without the bar tells how the transformation is applied to that particular point. So for example, if I take these weights omega, which are actually this color map right here, to look like that, okay? At the beginning, the weight omega will be 0, which means I will listen to the transformation T1 applied to this point and that point, for example. While if I'm on the right side of the object, the omega will be 1, so that one will be 0, the second term will be 1, so that point will listen to the transform T2. Okay, and that triplet of transformation, the only thing it does is it takes a point, it writes it in the coordinate frame of one of these T-bar, then you apply a relative rotation, and then you write it back into original space if you want to know why there's 3 of them and why they look like that. So if I do that, then I can actually obtain some form of deformation by simply applying that expression. And again, I think I have a chunk of code for this, for literally 3 lines of code to run this example, which is, I think, is pretty neat because you can do it in class during the course. And this is the case where T1 is identity, right? So I didn't move this node, and T2 was a rotation by 90 degrees. This is verbatim from the first equation, right? So this is a model of the transformations that you can apply to a surface. Now, differentiating through this adds a little bit of overhead, so I'm going to take a slightly simpler case. I'm still going to have multiple transformation matrices that I can optimize with respect to, but I'm going to consider the case where the weights omega I for a particular point are either 1 or 0 in the case of 2 transformations, or are Dirac functions for one particular transformation. Okay? And in the general case, you do not only have 2 transformations, but what you do is that you have something that's called a kinematic chain. So think about your hand, the position of the point Zi on the tip of your finger is affected by the global rotation of your wrist, the abduction, or I forgot the 2 names of these angles, plus all of the angles along the chain, right? So you actually have to accumulate the transformations, and that's what this productory here does. It accumulates all the transformations along the chain. So the transformation of Zi will be the transformation of this node multiplied by that, multiplied by that, multiplied by that, multiplied by that. And this number actually tells you how many degrees of freedom each joint has. Okay? So now, the problem of doing matching, let's say that I have a point on a depth map yi, which is this guy, then it becomes, okay, take the point on the depth map and project it onto the model. And now this is not a rigid model anymore. It's not controlled by only rotation and a translation. It's controlled by a set of parameter theta. So what you do is that you want to find the point yi that is close to the posed model given parameter theta. So for this point right here, Zi, if there was like a surface built around it, would actually be the closest point onto the surface. Okay, and the other thing to keep in mind is that because the point Zi is located is bound to this bone essentially, you're going to have to take in consideration of all of these degrees of freedom during the optimization of the transformation. Right? So there is a discrete set which is part of that kinematic chain function right here. So this one will tell you which part of the kinematic chain you're listening to for a given point, k, which is fixed in most cases, so you don't have to worry too much. So let's say that we're doing tracking only, we're not doing calibration, so we're only trying to look for the transformations t, not the t bars. And we have this kinematic chain. And now do you agree that the projection onto z, it's a point zi, right? I can compute it by projection, so I can bake my mesh in a certain configuration and then project onto that mesh, right? Given some parameters theta that control how the surface is deformed. Is that clear? So I take my rest configuration, I pose it in a certain configuration given parameter theta, then I have a point in that same coordinate frame and I project onto the deformed surface. That's exactly what this Zi is expressing. Okay, now Zi is a function of theta, and if it was a linear function, then we could just do a least square solve and it will be the end of the day, right? We would be done. The problem is that that function is nonlinear. So let's see what it looks like. So I'm going to consider, this mesh, or this is a collection of cylinders, it doesn't matter. It's bound on top of the skeleton and is abstracted for, let's say, this finger as this configuration right here, right? So these 3 communicate to each other, essentially, in abstraction. So let's say I want to minimize the distance in between that point and that point. And the degrees of freedom that I have to perform that minimization is the rotation and translation of the point, the rotation of that point, and the rotation of that point. Right? So I'm going to have to play with those 1, 2, 3, 4, 5 degrees of freedom to minimize the length of that correspondence. Okay, so if you don't remember this from your introduction to animation or similar courses, so the z function, the function zi, because it's nonlinear, or optimization actually, that depends from the route that you took. The function zi is nonlinear, so you cannot solve that directly. But what you can do is that you can compute a Taylor expansion of the function zi about the current configuration. Okay, just like we did before for point to plane, or for the rotation optimization. And now what I can do is that I can write the Taylor expansion, which is the current configuration, and I like to look backward when I talk about because I'm optimizing for the Zi in my notation. So I look backward at the previous configuration, and now I'm optimizing for a perturbation of rotations, and this is actually the Jacobian of that particular point, of that particular residual, which is actually relatively straightforward to interpret. I think I have it on this slide or on the next. Yeah, I probably have it on the next. I'll show it to you in a second. And the idea is that right now, the optimization has changed from the optimization of a single parameter theta, which will be my global solve, to a perturbation delta theta. So it becomes an iterative optimization. Okay, and then when I compute, so now this problem, sorry, I'm going to backtrack. This is just a matrix of constant. These are constant. These are constant. The only degrees of freedom are the delta theta. And you agree that this function is actually linear in delta theta. So this is a linearly squared problem, which you can just solve with the normal equation. You don't have to do anything special. And once you obtain the perturbation of the parameters delta theta, you can apply them to the previous configuration, which was this one. And you obtain, after a few iterations, you obtain your alignment. And just like before, you have to be careful that your Jacobian matrix doesn't do too bad of a job in describing the rotations of your points, right? Because these are a linear approximation of motion, so you want to keep your perturbation of the system small, so you typically have a penalization that also helps keep things nice and not exploding in your face in terms of optimization and condition numbers, if you want to look at it from the point of view. So I don't have the demo because my core plan. But the idea of what these Jacobian matrices are, it's pretty straightforward. So you have this point z of theta, which was this entire block right here, okay? And now what you want is that you want a linear behavior of that point under a certain rotation. So I look at that point right there, and I'm computing the Jacobian with respect to that point and with respect to that rotation angle. So the only thing that I need to do is that I need to explain the movement of this point, the linear movement of this point, as this degree of freedom is changing. So like before, I will have a rotation of that point, and instead of doing a rotation, the Jacobian for that degree of freedom, sorry, for that point and for that degree of freedom will be this tangent line right here. And because it's tangent to that circle, then you know that you can compute it as a cross product in between the normal, I'm going to use my cone, the normal of the point and the vector connecting the center to the point. And the magnitude, which is the amount of space you will travel as you vary theta, will be proportional to the magnitude, to the radii of the circle, which is simply the length of the vector. Okay, so it's not that terrible, right? You basically have to, you can actually do this in different ways. This is the geometry way of looking at the problem, and actually simplifies your life a lot. If you can explain the geometry, then you can actually write down the algebraic counterpart relatively easily. All right. So now we have pretty much everything. So you could repeat exactly the same process for most things that you do registration on. Even if you have some form of non-rigid deformation model, what you have to do is that you have to construct the linearization of the model. So you typically have to write the Jacobians, which are gradients with respect to the residuals of Fourier problem. You stack them in some matrices J, which we'll see in a second, or not maybe. And then you solve the problem as a linearly square optimization. Right? You get an update, and then you repeat. Pose the model in a new configuration, compute correspondences, compute the Jacobian, compute the new solution, and rinse, repeat, recycle. No, wait, I missed something. What is that? Rinse and repeat. I mixed two different expressions. Yeah, so I think this, I don't know why I went back. All right, so now, this is actually a paper that we had 3 years ago at SGP. We were doing hand tracking, so we had a camera. This camera will have a color image, which we'll use basically to identify the silhouette, which is the 2D part of the optimization that we were talking about earlier. As you can see, the optimization consists of a bunch of terms. These two terms right here are these monocular Hausdorff metrics that I was telling you about earlier, which this is the nicest way of explaining why there's two terms and why you actually need two terms that I could find. You can find some other term another way, and it would be nice if you can show it to me one day. And then what we do is that we can actually add another bunch of energy that describe what type of process we're looking at. So these are the priors of our transformations. So for example, we can say, do I have little videos for that? We can say that typical human hands rely in a manifold of feasible poses, right? They're not an octopus shape. They are relatively regular in their pose. You might say that people have physiological constraints. They cannot bend their finger backwards. You cannot have fingers that interpenetrate each other because they're made of meat and not of thin air. And you might want the smooth through time to be, the motion through time to be smooth, right? And you can add the list on and on and on. And you can do whatever you want. You can even add constraints that come from external sensors like Vicon systems with trackers and so on. And now the point is that you're left with this pipeline, which is actually very homogeneous in its structure. So every term right here, every single one of these terms, the only thing that it does is that with respect to some degrees of freedom, it needs to write the Jacobian matrix. And that's the only thing that you need to do. So if I want to edit my system so that I need to, for example, insert a color term in my optimization that also makes sure that the colors in between correspondences are matching with each other, then it will be another energy term. And because of the structure of linearly square, you can actually decouple these terms completely one from the other. And you can solve each of these terms independently, or you can assemble each of these terms independently and actually fracture the computation in between even different architectures if you want. So for example, these terms are here. We were running them on CPU because computing them took less than that, 100 microseconds, and with brutally written code, right, to obtain all of those priors, while the terms that depended on the data had tens of thousands of constraints, because every time that you have a point in your point cloud, you have a Jacobian entry corresponding to that. And then once you assemble the Jacobian matrix, you have to take the inner product of the Jacobian matrices. So there is like dense, expensive operations you have to do right there if you have tens of thousands of points per frame and only about 60 milliseconds to call it a day in terms of computational time, right? So that's why we did it in this way. Because of the structure of the problem, you can split them into different areas, into different architectures. And this is actually just to give you an idea of what the functions actually look like. They're not that hard. Like this is to achieve essentially angle bounds. So we're basically controlling that my parameter theta is within the range theta upper bar and lower bar. And in the second in which it is not, we penalize it with a barrier constraint. So this is a conditional Jacobian entry. So, but it's still quadratic in nature. So it's still differentiable because it's a flat function, and then at 0 it becomes a quadratic, right? So it's still differentiable. Then we have things like, yeah, I forgot that I had the plot right there. So that's what it looks like. And that doesn't happen, right? So that's why you want to add these into the system. Yeah, that's a bit of a brutal, I forgot that I put that in. Other things that you want to do is that you want to avoid interpenetration. So let's say that you abstract fingers like that. You want the distance in between two centers to be larger than the sum of the two radii. And again, that's actually how you embed the constraint into the solver. And again, it's differentiable conditionally, because when they don't overlap, you simply turn it off. So it's again a barrier. You can do things like optimizing for the smoothness of the motion. And this is nothing else than the temporal appellation operator, right? So you take concatenate your positions over time and just take a differential over second order derivative over time of a few points. Yeah, so, and you can penalize both velocity and acceleration. As I said, it's very generic as a, or one of the most important is that you can constrain your model to lie in a certain manifold. And this was, I guess we didn't start working on machine learning at the time yet, but this is a way of actually applying something that's called the Hausdorff metric. So given the average pose in your data set, you can actually build a matrix H, which assembles a metric that allows you to tell you how far the current pose that you're optimizing is far with respect to some rest configuration or to some Gaussian distribution that explains your data set. And actually computing this metric and embedding it within the solver, again, is not a big deal, because as far as you can factor the matrix A, it's linear again. And the matrix H is usually relatively small in size. And the reason for which you want to do it, beyond the fact that you want to reconstruct a pose that corresponds to the one of a human, is that it helps when you have an underdetermined problem. Like, so assume in this case, in this frame right here, we didn't have any data in this area, and the tracker was just like binding to some random noise into the sensor, and then just constructing a pretty weird configuration with minimal evidence to do so. So these statistical priors help you to in-paint your data whenever you have an ill-conditioned problem, if you want to ever use it. And there is a paper from Michael Black that does it in a prettier way than we did it, but it's roughly the same thing. So if you put all these things together, and I don't skip a frame, this is actually what you obtain. So we actually gave this demo at SGP, although if you tried it, we were publishing the code, so we used a sensor that was still on the market, and the performance on the Sense 3D, it was a different type of sensor, so it was a bit terrible, but still reasonable. The problem of this sensor, which was the Carmine, was that when you pointed a finger at the screen, like if you pointed it at the camera, the finger will disappear, and there is not much you can do, because the spatial pattern was defined for long-range acquisition, not for end tracking, but this is actually where the performances that we measure from an external camera in all these scenarios. And now the question I can tell you, and I think I still have half an hour, my internal estimate tells me, yes? Is that, okay, this is what I showed you right now. So each point can be expressed as a chain of rigid transformations, and I want to use the chain of transformation to figure out how to pose the object to minimize my alignment residuals, right? Now I ask you, well, along this continuum, and I've not seen a paper that does it on triangular meshes yet for this case, on this continuum, you might have like, subdivision surfaces, which are infinitely smooth and precise on that side. You might have some advanced version of the formation like implicit skinning, or you might have a triangular mesh. So how can we find something that lies in between that one and that one? And the core problem that we had is that the geometry of this tracking object was fixed in our experiments. So we had to adjust it by hand to match a certain user. Okay, and we'll see why later. And the question is like, what can we put there to kind of find a different way of representing geometry that is still real-time optimization friendly? And the answer that we had was to actually be inspired either by the way in which artists design simple pose models, right? They use these sketches where they draw these quasi-ellipsoids to describe shape, and then they start adding details on top of that, or at least that's how you're taught. Or the other inspiration was because we didn't know of Thierry. I don't know the first name actually, I only know that. But you can actually look at ZBrush, and there is a component called Z-Sphere, and if you want to assemble the very rough topology of an object before you start sculpting, you can actually use something called Z-Sphere, and from what I heard from a few animators, it's actually quite common, or modelers, it's quite common to use it to build a first version of the mesh. So now the question that we had is that, okay, can we actually take that and generalize it for tracking? Because that actually can be adjusted to any geometry that I want. And the answer was that, well, actually, that gives you a little bit of an idea of where I'm going. And the general purpose kind of modeling metaphor that we had was, well, we actually have something that is called the medial axis, which can be interpreted in different ways, but one that is particularly interesting is that it can be seen as the union of a bunch of spheres. And now we can take these construct from geometry and can generalize it a little bit. Just like triangular meshes are a linear approximation of a surface, what we can do is that we can generate a linear approximation of the medial axis. So we can coalesce a bunch of spheres of different radii in elements where all of the circles along this segment will have a radii which is interpolated along the segment. So geometrically, it's the convex hull of two spheres, but there is like 2 or 3 different ways of writing it: as a conic, as a linear blending of radii, and a union, a bunch of different ways. So that's the idea. Is like now we have that, and because medial axis is actually a generic approximation of the surface, you can do anything that you want in theory. Maybe not particularly well, but any solid geometry can be represented via medial axis. Then we can actually use this to construct tracking models. And the idea is that because to represent a 3D object, medial axis only presents manifolds of, what's the exact term? Basically, they can only be surfaces, segments, and points. There are only 3 primitives that you can have in a medial axis. Therefore, to represent something like a body or an arm, the only thing I need is a triangle with a radius function defined thereon, and a segment with a radius function defined thereon. And now I'm able to represent any piece of 3D geometry that I want, given enough segments, points, or triangles, and the radius function defined thereon. Okay? And the other cool thing is that, remember, one thing that we want to do is that we want to take a point and we want to project it onto the surface. You might say for this conic surface might be difficult. No. Actually, if the shape is constant, and beta is like the tilt angle of one of these planes over there, you can see it is this angle right there. If beta is fixed, this arc sine, this tan give you a constant in output, and now the projection onto a capsule is 2 lines of code, which is actually multiplies and adds, and that's it. There is no iterative operation in that, so it's extremely fast to compute the correspondence. We actually didn't do it like that in our code base, but it's still fast, but this is actually the fastest way that we're using recently to do it. And then what we can do is that we can define, we have primitives that look like that. So this is a segment, that's a triangle with radii. We can actually build a topology that looks like that. And then whenever 2 spheres are connected by a segment, I instantiate implicitly a function, right? I don't have to create the mesh, but implicitly I'm defining that the actual surface that I want is the union of these convex hulls of triplets and pairs. And I obtain a model like that, which you can see has not many elements. And if you want to see the effect, in this case we were trying to break it. Like that's a disclaimer, we were trying to break it. But you can see that because the model, it was not a perfectly good fit to the person, and we're not using any machine learning right here, it's pure geometry running, right? But because the model was not a particularly good fit, you would underfit the data, and that causes correspondences, these ICP correspondences, to fold on the wrong part of the surface, and it will eventually guide you to the wrong configuration, or to a wrong local optima, to a local optima that was far from the one that you wanted. Okay? So you cannot see the point cloud almost anymore in this tracking, right? So Anastasia spent a bit of time to design a template that really, really was able to capture the geometry of her hand. And now, what I can do is that I can generalize my tracking problem a little bit. Okay? Before, we were only looking for transformations. So I wanted to find the pose parameters over time, this theta over time t, in such a way that my model will fit the measurements. We can actually see as these points that are appearing over here. But now we have another problem. So now we have a geometry that we can parameterize. So one we can adjust to a particular user. Okay? So now we have another set of parameter beta that build a shape space amongst different people. So now I can adjust those parameters, which are the position of these vertices in this sphere mesh, as well as the radii, to personalize it to somebody. Okay? And why is this popping up again? So what I can do is that I can actually treat this as a bundle adjustment problem. So, well, bundle adjustment we tend to call it like that, but basically an optimization over a collection of frames rather than over a single instance, or an optimization with respect to a full point cloud, not just a monocular point cloud. And not just at a single time frame, but at a collection of time frames. Right? So this is a global optimization through space and time. Okay? The shape B will be constant because it's the same person assuming different configurations, while the parameters theta n change over these 4 frames. Right? So I want to figure out what are the tracking parameters so that I can then figure out the shape parameter. So I can adjust these templates to a particular person. And if you actually look at the way in which people have been doing that, I guess these are mostly CVPR papers, and it was Microsoft at the time. They had 3 papers on the topic. It was pretty complicated. You had to take a mesh. You had to align it to some complete measurements that you had. You had to build a statistical space. You have to optimize within the space. It was a bit of a hustle. And what we actually found out is that beyond the fact that my PhD student did not want to go through the hassle, but what we found out is that by simply building an algebraic, i.e. hand-tuned shape space, which simply says that a generic model, most of the time, can actually be seen as an anisotropic scaling of the parameters in your optimization, right? So the difference in between me and Alec is that Alec is a little bit taller, and because he's a little bit taller, you expect that most of his bones would be proportionally longer than mine, right? He will not have legs that are twice my length and arms that are half. So that would be a pretty weird Alec. So that's exactly what this is encoding. And because of that, plus the fact that sphere meshes already were heavily subspaced in the type of geometry that I can capture, with a 5 DOF shape space that you can build, that you can see right here. As you move left to the right is the pound size that is changing. Top to the bottom, I think, is this overall size. And then the R is along the radii, so thin fingers, thick fingers along that direction, right? So what we did is that, well, what you can actually do is that first, I can force my solve to act in this shape space. And then once I reached a local optimum of that optimization, I can actually relax the entire problem and let it converge to something that is more refined. And that's it. We actually beat the quality in terms of registration compared to the 3 papers or 4 papers that I had. And we didn't have to go through all the pain of acquiring a data set. What this is telling you is that the hardest part in building a shape space is actually getting the initial coarse registration. And this is often enough if you do things like bodies and hands, okay? Once you have that, then you can do the refined adjustment and build maybe a more detail-oriented shape space. And the other thing that boils down is that, remember the tracker that I showed you earlier? What's your estimate on the number of lines of code of change that reparameterizing the problem like that does? 1. With 1 line of code, we will be able to incorporate essentially the work of 3 different papers. Right, so we show these in our paper from CVPR from last year. But it's pretty neat, right? So it's 1 line of code, and you subspace the entire thing, and you actually do coarse deformation before you do fine deformations. And you can have a hierarchy of them. We didn't explore that direction, but because we were already producing models that were pretty nice. So this is, however, just to say that, this is calibration, so we're optimizing for the beta and the theta because you have to do that, but it's done as a bundle, right? So it's done over a collection of that maps D. Okay? That means that to be able to construct a template for my body before I'm being tracked, I will have to go in front of the camera, assume different poses, collect the couple of frames, slam everything into a large optimization problem, and then get the solution out of it, which, according to how many points you add, might take, maybe not that long, but it's not really a convenient way of doing it. However, what you can do is that you can say, well, what if you take your optimization problem, and now you rewrite it a little bit. You allow the shape parameters to change over time, okay? And then what you want to do is that, let's say that you have a process that in a particular frame is able to make certain guesses about the shape parameters that you have, right? So if these are the shape parameters from the past iteration, these are the shape parameters that the current iteration of the solver is telling me. Those, I think, are the ones that you should adjust. Now, you can guess that, let's say that if this estimate gave me a good choice, right, then I want this weight to be high. While if these estimates were done particularly bad, for example, how long, where is my, well, I guess you can tell, but where is my wrist, right? It's a kind of a heel pose problem, because my elbow. My elbow will be the center of rotation, and if arm is straight, you can all localize it very well. If I bend it, it's very easy to localize. So the idea that we had was that, well, if we can infer the length of this bone in this configuration, but not in this configuration, what is this function right here that tells me that one configuration is better than the other? And what we actually found out was, again, I think quite beautiful, is that the Gauss-Newton or LM solver that we were using, if you think about it in terms of optimization package, that solver, once it's converged, it doesn't only give you the solution of the problem. It also gives you an estimate of the uncertainty of the problem. So you can see it over there. What we're doing is that we're trying to infer the parameter, the length of the first phalanx, the beta 1. And when the finger is straight, as you can see, the registration energy with respect to the point cloud that I have is relatively flat, which means the problem is badly conditioned. While when I'm bending the finger, you can identify the center of rotation pretty well because you have a much better conditioned system. So at the beginning, we were asking, okay, what actually are these functions? And maybe we can learn them from a data set. We can just perturb, check if I can recover the parameters, and then build a database that says this pose is good for doing the inference or not. But it actually turns out we didn't need that. And actually, our LM solver already contained that information. So the only thing that we needed to do is that we needed a way of identifying what this function was. And I'm pretty sure I didn't add the slide with the math. So this was a Sigraphesia paper from last December, I think. I'm losing track of time. And what it does is that it basically monitors per frame what degrees of freedom are actually a decent or can be inferred in a decent level of accuracy. And only in those situations, it actually integrates that guess through time. And we actually reconnected this to be a form of Kalman filter to solve the bundle adjustment problem that we had, okay? But without having to take a collection of frames. It's a streaming framing coming in. And the other nice thing, as you can see, the model after a few frames is actually recovered to be, so let me just replay that one. So as you can see, the base shape is actually being optimized over time. And after it reaches a certain level of saturation, it said, okay, I'm done. And the cool thing is that that expression that I showed you earlier can be connected directly to be a form of Kalman filter. And if you have ever tried to code up Kalman filter, is not really the nicest piece of code you will ever write. But yet again, we were able to do it directly within the LM solver. And again, if you embed a Kalman filter directly within the LM solver, and if you have these covariance matrices that come from your Jacobian, as is explained in the paper, the only thing that you need to do is that function right here, rather than being an element-wise B, will be a vector over here. And this function here is a covariance matrix that comes from your Jacobians. And the only thing you need to do is that you need to accumulate this Jacobian as information is coming in. So basically, you have a way of writing the most advanced version of a Kalman filter, which is the Leven-Normal-Quad iterative extended information form Kalman filter. It's like I'm running out of memory in remembering the name. But again, the cool thing is that it's a relatively advanced concept, but it embeds in your solver in one line of optimization, which I like, because then I don't make coding mistakes. All right. So can I get time so I can make an estimate? Okay. So one final part, maybe I'll skip the very, very final part, but one thing that Alec was noticing earlier, and Keenan and Pierre, is that, okay, fine, now we have this energy, these defined correspondences, but what if these correspondences are wrong, right? So we knew that if we have perfect correspondences, we can converge in closed form for the rigid case. And now the problem is that these correspondences often are not correct, right? Because this is an iterative optimization problem, so the closest point correspondences that you established might have mapped to the wrong location, or might have mapped to an outlier, right? So you have one outlier in the system that wants to attract the model to be close to it. So how do you avoid that problem from happening? So remember, we have the transform point, we have the corresponding point on the surface, and now what we can do is that we can add a correspondence weight here in the front. And people in the past have done a lot of manual heuristic tuning of what the weight omega I is. One form was the normal orientation discard that I was mentioning earlier while talking with Michael. But there is actually a proper way of looking at a problem from a statistical point of view. So, and I think I'll just unroll this slide. So now the fundamental assumption when you solve a linearly squared problem, so you're going to do a perfect job if your residual are going to be distributed as a Gaussian. So you can reduce least square to a map or to a ML, or it depends if you have priors or not, either a map or a maximum likelihood with a Gaussian prior on the distribution of your residuals. Right, so this too is actually what is causing most of your problems. When you have noise and outlier, that too is what it's forcing you to overfit to noise and outliers and to consider those values as being important for your optimization. And what I can do is that maybe I can leave this to be a 2, and what if this weight omega I could be set to 0 whenever I think I know that a point is an outlier. So now can we define a process that determines that function omega I in an automatic way and in a way that is meaningful? So that's what we're trying to do. And if my slide would play, so you can use heuristics, and these are just a collection of them. The paper from Simon lists a dozen that you can refer to. And what I would like to take a look, though, is that if I start from this configuration, and let's say that I have that measurement of my surface, and now I might have noise or outliers, like these points right here, or I might have a piece of the surface that is not corresponding. Right? That is not, I don't have a measurement for the part of the surface because the Kinect sensor was not able to measure it. So what happens in that case? You're going to run your closest point correspondences, and what will happen, this will happen. Some of them might be lucky, and they might be hooking in the correct configuration. Other ones, because I didn't have that chunk of blue surface right here because it was not measured, they're going to generate massive outliers. Okay? So now if I try to solve the optimization that I showed you earlier, nothing works because you're basically considering even a single outlier point can destroy your entire optimization. And we'll understand why that is in a second. And the reason for which that is the case is because our matching energy measured the length of these residuals and included them in the optimization as a square function, right? So think about, this is a function that you plug in the length of one of these correspondences, and the function tells me how much the optimizer cares about the residual being minimized. Okay, so if I have these points right here, these points will map in this location, and now you can look at the gradient of this function, right? The gradient will tell you how much the optimizer will respond to that certain residual. For a small residual right here, you're going to get a small gradient because the function is flat. And for a very large residual, so for example over here, you're going to get a massive gradient. And the further you move away from the origin, the larger the gradient will be. So the largest gradient in a least square with noise and residual will be the biggest outlier that you have in the system, which is not a good idea, right? That means that the optimizer is going to care the most about the biggest outlier that you have. And I'm going to shorten it a little bit, so that's exactly what I said. One way of doing will be trimming the outliers, so deciding maximum distance after which you discard it. This is the same thing as scaling the gradients with a function that looks like that. And the point, okay, let me just, I don't want to take too long. The point is that rather than optimizing for a linearly squared problem, what you can do is that you can map this into the minimization of another robust function. So you remove the square essentially and you replace it with a function phi. And we'll see what these look like in a second. And the idea is that if you do that for a particular class of function phi, I think they have to only be differential if I'm not mistaken, what you can do is that you can rewrite the problem still as a linearly squared problem, and the only thing you have to do is that you plug a weight function in front of it. And the second thing that you need to do is that for that version of the linear problem, you're not going to get a solution in one shot, but you're going to have to iterate a few times before you actually get the optimal solution. And now you might ask yourself, it's like, fine, if I plug phi and phi is something else like the robust function, I could come up with a weight function for that problem. Now, how do I design it? And here is where I'm skipping, and I'm going to refer you to our registration notes. But the idea is that there is a class of functions that are called M estimators. And what they do is that they basically assume that your residuals will distribute in a certain way. And according to the type of estimator you pick, you're going to have a corresponding weight function that you can plug in front of the optimization. And the ones that I'm using these days are one of the two. One that is easy to implement, one is a little bit harder, and we have no consensus on which one is better. I'm going to show it to you in a second. So the first one is the p-norm, which is this one right here. Okay? All right? And what happens is that you convert essentially the least square problem, which is this configuration. So the least square problem is like you have p equal to 2, so you have a square function on one side, and the corresponding weight function will be flat. Like every point enters the optimization with weight 1. Okay? And if I change the power of p in the p norm, that function phi will change shape to do that. Okay? It's becoming more and more non-convex, like to the point of being Dirac non-convex, like only at one point. And the weight function will be some expression that looks like that. Now, how do you interpret this in this particular case? Assume that you have two objects, and for example, you have missing pieces of information on the two objects, so you're trying to align them. So there's going to be regions that overlap perfectly, and you're going to get 0 residuals. And there are regions that are in complete non-overlap because there is no data, and they generate massive amount of outliers. If you have a solution that is locked in, that is currently in an optimal configuration, you're going to have a lot of points with a 0 residual that are going to be located at this point in the kernel function, which means that they have a weight omega of x which is infinite in the limit, right? If they have a 0 residual, it will be infinite, which means that those points will be infinitely considered inside the optimization as being fit to. While for large outliers, which will lie over here, as you can see, the gradient of the function is almost flat, which means that it will be mostly ignored. Not completely ignored, mostly ignored. So this is one way of doing it, is using p-norms. The other one is the Giemann-McClure kernel, which I think is pretty popular. And we have a discussion on which one is better. Like some people say that this is not particularly friendly because the shape of this function doesn't look like what Gauss-Newton expect, which is a quadratic function at your optima, while the Giemann-McClure is a bit of a smoother kink at the origin, but is roughly doing the same. And now what I want to show you is 3 configurations. So this is the initialization of ICP. I'm doing only rigid in this case. And by the way, this generalizes to the non-rigid case, right? So this is a completely generic framework for robust optimization. This initial configuration, first optimization will be least square. Second one, I will discard correspondences longer than a certain value, which is this value right here. Third one, I'm going to use a p-norm with a 0.4 coefficient, which you pick, essentially. And this is what happens. First one gets stuck completely. Second one will get still stuck, because it's basically these points right here are not entering the optimization because they follow on the right-hand side of the function. And the p-norm, on the other hand, has gradients that do not vanish completely. There is still a little bit of a gradient left on the right-hand side. And it can actually, right, this one that I made. And it can actually lock into the solution. Right, so the parts that are overlapping perfectly will be falling in that area, which means that the function omega for those points will be extremely large. While for these points here in the yellow area, which will map to the boundary of the blue area, those will have a large residual, therefore a small gradient. Okay? So to add this to your optimization and get a robust solver, the p-norm is one line of code that you have to change. Right? The function has to be 1 over the normal residual for L1 and a version of it with the p included for the rest. I can refer to you to the paper if you want to look at it more. And you can actually do stuff like this where, you know, you cannot even see what